I'm analyzing a dataset. It has 100 samples and describes things using 5 different features. Think of it like having 100 people, and measuring 5 things about each person, like height, weight, age, etc. This simply restates the dataset characteristics. 100 data points, each described by 5 features. We're asked to determine which statements are correct about the covariance matrix. That matrix summarizes how the 5 features relate to each other, how much they vary together. We will use MinCovDet from Sklearn to calculate this, which is a special way of calculating it. This statement is true. Because we have 5 features, the covariance matrix will always be a 5 by 5 square matrix. Each entry describes the relationship between a pair of features. This is false. MinCovDet specifically aims to create a non-singular, invertible, matrix, which is essential for many statistical analyses. Absolutely true. That's the whole point of using MinCovDet. It's designed to minimize the effect of unusual data points that might skew the results. This statement is false. MinCovDet uses a clever subset of the data, whereas NumPyCov uses all the data, making them likely to produce different results. I'll be using MinCovDet, minimum covariance determinant. I'll fit it to my data and then examine the resulting covariance matrix. I'm analyzing a covariance matrix produced by Sklearn's MinCovDet estimator. This estimator is designed to handle outliers in datasets. We'll examine the properties of this matrix. This statement is true. Because I have a dataset with 5 features, the covariance matrix will always be 5 rows by 5 columns. A covariance matrix always has dimensions equal to the number of features in your data. Think of it like this. Each row and column represent a feature, and the entries show how those features relate to each other. This statement is false. MinCovDet specifically aims to produce a non-singular, invertible, covariance matrix. It's designed to avoid singularity, even if outliers are present in my data. A singular matrix is one that's not invertible. You can't get back your original data. This statement is true. That's the whole point of using MinCovDet. It's designed to be robust, which means that it gives a good estimate of the covariance even when there are some unusual data points that could skew the results. I want to use MinCovDet to protect me from those outliers. This statement is false. NumPy.cov calculates the standard sample covariance matrix, using all the data points equally. MinCovDet is different because it uses a subset of data that minimizes the effects of outliers. I want to choose the method that works best for my specific data. I'm analyzing a covariance matrix created by the minimum covariance determinant, MinCovDet, estimator. This estimator is a fancy way to calculate the spread of data, but it's special because it's really good at ignoring outliers, those unusual data points that can mess up a regular calculation. We'll examine how this affects our results. I have 100 different data points, and each one has 5 different measurements associated with it. Think of it like 100 people, and I'm measuring their height, weight, age, blood pressure, and income. Each measurement is a feature. I'm using the MinCovDet estimator, a tool that's great at finding the covariance, how the different features relate to each other, even when some data points are way off. It's like a super-powered statistical detective that's not easily fooled by misleading data points. Because I have 5 features, the result will be a 5 by 5 matrix. This matrix shows how each of my 5 features relates to every other feature. For example, it will show how height relates to weight, height to age, etc. It's a super organized way to see the relationships. This is true. Since we have 5 features, the covariance matrix will always be 5 rows by 5 columns. It's like a square grid showing all the relationships between the features. This is false. A singular matrix is one that's not invertible. You can't easily undo its effects. MinCovDet is designed to avoid this issue. It aims to create a matrix that's always invertible. Absolutely true. That's the whole point of MinCovDet. It's built to handle those pesky outliers that can throw off your results. It cleverly minimizes their impact on the final covariance calculations. It's like a filter. This is false. MinCovDet calculates the covariance using all the data points equally. MinCovDet is smarter. It focuses on the most reliable data to get a better result, ignoring any outliers. I'm analyzing how scikit-learn's MinCovDet, minimum covariance determinant, handles covariance matrices, focusing on its robustness to outliers. We're using MinCovDet, a tool that cleverly finds the best subset of data to estimate a covariance matrix. It minimizes the impact of those pesky outliers that can skew results. I've got a dataset, 100 data points, each described by 5 characteristics or features. Think of each data point as a person, and each of the 5 features as height, weight, age, shoe size, and income. A covariance matrix shows how much the features vary together. With 5 features, I'll get a 5 by 5 matrix because each feature's variability is compared against every other feature's variability. I'm checking if the resulting covariance matrix from MinCovDet will be a 5 by 5 matrix. This is true. The size of the matrix directly corresponds to the number of features in our data. I'm asking if the covariance matrix will be singular, not invertible. MinCovDet avoids this, making it false. Here, I want to know if MinCovDet handles outliers well. Yes, true. That's the whole point of using MinCovDet, to be robust to unusual data points. Lastly, I'm checking if the covariance matrix from MinCovDet is the same as one calculated using NumPy's built-in covariance function. No, false. MinCovDet uses a subset of data and is specifically designed to be different. I'm analyzing the properties of a covariance matrix calculated using the minimum covariance determinant, MinCovDet, estimator. This estimator is really useful because it's designed to handle datasets with outliers. I'm working with a dataset containing 100 different samples, and each sample has 5 different features or characteristics. Think of each sample as a person, and each feature as something like height, weight, age, income, and shoe size. Because we have 5 features, the covariance matrix will be a 5 by 5 matrix. Each entry in this matrix tells us how much those pairs of features vary together. For example, one element represents how height and weight tend to vary together. This is true. A covariance matrix for n features is always an nxn matrix. That means if we have 5 features, the matrix will have 5 rows and 5 columns. This is false. A singular matrix is one that's not invertible. You can't easily undo its calculations. MinCovDet specifically avoids creating a singular matrix. It's designed to give me a useful, invertible matrix, even with outliers present. Yep, this is correct. The whole point of using MinCovDet is that it's robust to outliers. It minimizes the effects of unusual data points, giving a more reliable covariance calculation. This is false. NumPyCov calculates the standard sample covariance, giving equal weight to every data point. MinCovDet, however, is smarter. It downweights outliers to give a more accurate overall picture. I'm analyzing a covariance matrix created by the minimum covariance determinant, MinCovDet, method. This method is really good at handling datasets with outliers. We have a dataset with 100 different observations and each observation has 5 different characteristics we are measuring. Think of it like 100 people, and we're measuring 5 things about each person, like height, weight, age, income, and shoe size. Because we're measuring 5 features, the covariance matrix will be 5 rows by 5 columns. Each entry shows how much 2 features change together. For example, we can see if someone's height is related to their weight. MinCovDet is designed to not be messed up by unusual data points, outliers. It cleverly ignores or reduces the effect of those outliers when computing the covariance matrix. Think of it as a smart filter, making the analysis more reliable. A singular matrix means it cannot be inverted. MinCovDet avoids this problem. It usually gives a non-singular covariance matrix, which is good for most statistical analysis. Nope. The standard numpy.cov function uses all the data points equally when calculating the covariance. MinCovDet is different. It cleverly chooses a subset of the data to reduce the influence of those pesky outliers, giving us a potentially better picture. I'm analyzing a covariance matrix, a key concept in statistics that describes the relationships between multiple variables. Specifically, I'm focusing on how the minimum covariance determinant, MinCovDet, method, a robust statistical technique, helps us understand this matrix. MinCovDet helps to handle data with outliers better than other techniques. I'm using Sklearn, a popular Python library for machine learning, to perform this analysis. Specifically, I'm employing the MinCovDet estimator. This is an algorithm designed to estimate a covariance matrix in a way that is resistant to the influence of unusual data points or outliers. I have a dataset with 100 data points, each described by 5 different characteristics or features. I will use this data to compute my covariance matrix. Because my dataset has 5 features, the resulting covariance matrix will be a 5 by 5 square matrix. Each entry represents the relationship between a pair of features. For example, the entry in the first row, second column shows the covariance between the first and second features. This is a fundamental property of covariance matrices. It's like a map of how features relate to one another. This is the core question that I need to answer. I will evaluate several statements about the properties of the covariance matrix I'm calculating, determining which are true and which are false based on my understanding of MinCovDet and covariance matrices. The key idea here is robustness. I'm looking for a method that isn't overly swayed by outliers, unusual data points that might skew the results. The MinCovDet method is designed to produce a covariance matrix that's less sensitive to the effects of such outliers. This is crucial for reliable analysis.